Hey guys, we're going to tackle something today that I think is rather difficult to understand. It's one of those things in calculus that why do we do it? Some people think, but I think it's important, and it's called numerical integration. You can see that, and we've done this before. We did it in Calc 1, the left endpoints, the right endpoints, the midpoints, the trapezoid rule, Simpson's rule. And what we're going to do is we're going to calculate integrals or the values of definite integrals using numbers rather than integration rules. All right, and we're going to take it a step further this year, and we're going to look at error estimations of each. And this is where the challenge, I think, will come in this section. So let's take a look at a couple examples. We'll look at the error estimation, and then we'll let you go. So we're going to skip doing the rectangles, the left endpoints, the right endpoints, the midpoints, because I think you know how to do this. But we're going to start doing one using the trapezoid rule. All right. And so if we graph this function, hopefully you know it looks a little something like this. And about here is -1, and about here is 2. And so we're going to calculate that area there by putting in trapezoids. And we're going to put in 6 trapezoids. So what that means is we're going to put in 1, 2, 3, 4, 5, 6, I believe we have that right there. So there. All right. So I think, remember what we're going to do is we're going to just make trapezoids. So we're going to look like this. 1, 2, 3, 4, 5. Yeah, there's 6 trapezoids there. All right. Well, you should know how to calculate the area of a trapezoid. All right. And so we're going to do this by hand. And so let's just do the first one here. Remember the area, let's just do the area of this first trapezoid right there. Okay, so its width, and the width of all of them is 0.5, and it has 2 heights, which we call the bases, and that is f of -1 and f of 0.5. And if we calculate those two, f of -1 is 2, and f of 0.5 is 1.25. Okay, and so then the area of that trapezoid is 1/2 times 0.5 times 2 plus 1.25, and that equals 0.8125. All right, now I'm not going to take the entire video to do that, but we're going to have 6 of those trapezoids. All right, and I'm going to show you what the calculation on Desmos is. So you can see the calculation here. Right, notice I did f of -1 plus, but I did 2 of these. Well, what's going to happen if we go back? Okay, if we go back, I have this one there once, but this one is in this trapezoid and this trapezoid. This one is in this trapezoid and this trapezoid. So the same for all of those red interior trapezoid boundaries. They're all there twice, but f of 2 and f of -1 are there once. Okay, I did 1/2 because that's the area of the trapezoid. You use 1/2. There's the width, and there are all the heights. I just did it all at one time. And notice this is the actual area right here, and this is my approximate. So I was off by 0.125. Now, we're going to let calculus tell us what should be the error estimates. Okay, so we know that our actual error here, all right, our actual error is 0.125. All right, what does calculus tell us our maximum error might be? So we have kind of a convoluted formula here. The maximum error in trapezoid, in our example, is 6 trapezoids we put in. So we put in 6 trapezoids. All right, and m is the maximum value of f double prime for x is an element So if you remember, our f of x is x squared plus 1. So its first derivative is 2x, and f double prime of x is 2. So let's start to fill these out. All right, so we have 2, and b minus a is 2 minus -1. That's cubed, all over 12, and we use 6 trapezoids squared. All right, and we're not going to worry about this here where this formula comes from or why it works. We're just going to use it. All right, so we're saying our maximum error here is 2 times 3 cubed over 12 times 36. And I'm working without a net here, mainly a calculator. That's right. Now let's see, we can work this out. And when we work all this out, we 0.125, if you believe it or not. So, so this divides this, and we get 6, and one of these 3's divides that, so squared, and 3 squared is 9, so it divides that, 36 and 4, so this comes 1/8. Okay, and so if you remember correctly, our error before was 0.125, as you see right here. All right, let's take a look quickly at Simpson's rule. Let's do the same thing with Simpson's rule. I'm going to make this a little bit more complicated of a function because Simpson's rule, if you remember, works with parabolas. So Simpson's rule, like I said, it uses parabolas to estimate the area under a curve, and I've changed my mind midstream here. We're not going to do an example of Simpson's rule. Let me just give you the formulas here, and we'll talk about it in class and look at it in class. I have the utmost confidence in your abilities to take what we've done and apply them to an example in class. So Simpson's rule says that the area under a curve, so the area under a curve is approximately, so it's this kind of funny formula. So notice that we alternate 4 and 2 and 4, and it's going to continue, but we always got to end with 4 here, all right? And then notice our smallest value and our largest value are in their ones, okay? So that's Simpson's rule, and recall, I'm going to say this again, it uses parabolas, and we'll talk about that in class. Now, the error of Simpson's rule is bounded by this. Okay, so we'll say that the error, okay, so the error is less than that. There's that m again, but with Simpson's rule, it's a little different. Okay, m this time, there we go, m is the maximum value of this time the fourth derivative of x, okay, for x an element of a to b. So it's got to be between a and b. All right, so there you go. Hopefully we can make this make a little sense to you. We'll talk a little bit more. Why? So the last question is why numerical integration? Okay, so why numerical integration? So let's take a look at a couple integrals on Desmos here. Okay, so this first one, the integral of 1 over 1 plus x squared is arctangent, and when we plug in 1 here, we actually should get pi, and we get that 3.14159266359. All right, so that's good. This integral is the area of a circle. It's actually the top half of the semicircle, but its area doubled should also be pi, and we get the same value. All right, now this one here, this integral, okay, this antiderivative, we're going to say, is the arc sine, but when we plug in 1, we get pi over 2, we double that, we should get pi. So for all three of these integrals, we should get pi, but yet we don't get the same value here. We don't get the same value here. All right. Now, so if we're going to program a computer to calculate these things, we have to have a way to do it. The calculator, it's a near impossibility to get the calculator to know what all these integrals are. All right, and so what we're going to do is we need to be able to program a calculator. So the question, why numerical integration? Okay, my best answer here is we need to be able to program a computer to evaluate integrals. And the only way we can do that is using numerical integration. All right. Hey guys, I appreciate you watching. I hope this kind of makes sense. Please, please, please ask questions. I know I went very long. So anyway, have a great day. We'll talk to you in class.